Okay, so we're going to talk today about energy and a couple different types of energy. Okay, energy in and of itself is such a broad concept, and it's realistically like the most important concept in science, right? Or one of the most important concepts in science, because everything stems from that in a lot of different ways, a lot of different avenues. So we're going to kind of break down or really zoom in on energy in a couple different ways. There's a lot of different types of energy that we could talk about. What are some examples of different types of energy? Kinetic. Okay, kinetic. That's one we're going to talk about. Potential is the other one. What are types like that we see every day? Right? Heat, electrical, right? Light, all these types of energy. Those aren't the ones that we're going to necessarily hit on, but those are all different avenues for energy, right? There's also that's energy that's transformed within your body, right? All this type of biochemical stuff that we can talk about energy in terms of photosynthesis is a form of energy, transform, all that kind of stuff has to do with energy. So it stems from, the very, very basics of life. Energy comes from. Okay, so we are going to talk about in this chapter kinetic and potential energy. And when we say translational energy, that just means, again, we're talking about things that move pretty simply from point A to point B. So we're not rotating yet or spinning yet, but they're moving from point A to point B. Okay, and we're going to have a transfer of kinetic and potential energy. Okay, so when we think about energy, the concept of energy in and of itself is the ability of an object to do work. Okay, it's the ability of an object to do work on another object. Okay, so let's break that down a little bit more. The ability of an object to apply a force that would cause that object to travel a distance. Right, does that kind of make sense? If work is equal to force times displacement, then the ability of an object to do work means it has the ability to apply a force to an object, which would then move that object a displacement. Right? Does that kind of make sense? That's the very basics of this energy that we're going to look at. Okay, so it's the ability of an object to do work. Okay, so you can ignore the equation here for just a little bit. We're going to work through kinetic energy and we'll get to our equation. But kinetic, in and of itself, what does kina usually mean? Motion, right? So the kinetic energy of something is the energy of it while it's in motion. So it has to be in motion for it to have kinetic energy. Okay, kinetic energy is very transferable, right? We can see it transfer from one object to another. And this chapter, we're really going to see that transfer. In the next chapter even more. We're going to see it in terms of momentum and collisions and all that kind of stuff. But where do we see a really clear picture of a transfer of energy? Yeah, like when you hit an object, you hit a ball, right? Think about specifically like pool balls, right? We hit one, usually one comes to a stop or slows down and speeds up another one, right? Those are examples of collisions that we'll talk about next chapter more in depth, but that's a transfer of energy. Same thing when you contact any type of an object, right? When you hit a ball, you hit a golf ball, any sort of contact that can be made and moves an object, right? We're applying a force to move an object a certain displacement. That's energy, right? So we're transferring that energy from one object to another. Okay? So when one object exerts a force on another and the second object is moved a distance, that means that work has been done. Okay, so these two concepts of energy and work are relatable in that way, right? Energy is the ability of an object to do work on something else. Okay, so here is our equation for kinetic energy. And sometimes you'll see it written as like just a capital E with a subscript K, right? I usually just do KE, and that's what your book shows it as, so I'm just going to keep it there. What do you think the M stands for? Mass. Good. So it should be measured in kilograms. And then V is velocity, and it should be measured in what?
Meters per second.
Good. Okay. Meters per second. So it's important here to understand only the velocity term is squared, right? Not the whole thing. But all three of these terms are just multiplied by each other. Okay, so it's still a big multiplication term. Only the velocity term is going to be squared here. Okay, so mass has to be in kilograms. velocity has to be in meters per second. Okay? All right, we already talked about translation. Okay, so we're going to look at how we can connect work with energy now, right? We said it's the ability of an object to do work, and so this is something called the work energy principle. Okay? And what it's telling us is that the net work that's done on an object is equal to the change in kinetic energy. Okay? The net work that's been done on an object is equal to the change in kinetic energy. So you can just pick one of these equations to put on your sheet, or both, or however you want to do it. Your book uses 2 and 1 for like final and initial. You can choose to do whatever you want there. Okay? But usually I always will just, whenever it's theta, right, it has to be final minus initial. So whatever subscript you want to use for that, whether it's 2 and 1, whether it's F and I, whether it's nothing and a 0, whatever you want to do in terms of final minus initial, that's up to you. But the net work on an object is equal to the change in kinetic energy. So whenever we see this delta, that has to tell us that we're doing final minus initial. Okay, that's really important. So it's not always bigger minus smaller, right? Always final minus initial. Okay. Okay, so that is one that should go on your equation sheet. Your kinetic energy equation should be on your equation sheet too. Do you want me to go back to that real quick? Yeah, I would grab a new one if you want. If you want to add to your old one, you're more than welcome to. But this chapter and the rest for the semester, you have quite a few equations. Okay, so this is cleverly named the work energy principle. Bless you. Okay. And this work energy principle only deals with the net work done on a system. Okay, so it's got to be the overall. It's not just the work done by friction or just the work done by the applied or whatever. It's the net work on our system. Okay? Sorry, do we have what we need here? Okay. So this is, you don't have to write this part down. I'm going to talk through this just a little bit. Okay, work energy principle tells us that positive network is done on an object, then the kinetic energy has increased, right? So let's just think about this. If net work is positive, then that means our final had to have been greater than, greater than our initial. Would you agree?
Yeah.
Okay, so if our net work was positive, that means we've had an increase in kinetic energy, right? We've either gained speed or we've gained mass, usually not mass, right? We usually don't add mass to things. We probably gained speed at some point, which gained kinetic energy, right? Which means that positive work has been done. So if negative work is done on the object, what does that mean has happened to our kinetic energy? It decreases, right? If we have negative work that's been done, we've had a decrease in kinetic energy. So usually that translates to the object has slowed down, right? If velocity is an essential component to kinetic energy, usually that translates to the fact that it's slowed down. Okay, if no net work is done on the object, then that means our energy has remained the same, right? We're moving at constant velocity, we're not moving at all. Whatever it happens to be, that means that no change has been done. Okay, does that kind of make sense with our networks system, right? We've had several examples in which our net work is 0, right? And that's usually the case when our object is moving at constant velocity or it's not moving at all, right? So that means there's no change in kinetic energy. Does that kind of make sense? Okay. Kinetic energy is measured in joules, just like work. Okay, so unit for energy, all these types of energy and work will both be joules. Okay, so capital J. Okay, and kinetic energy is also what we would consider a scalar quantity, which means it doesn't have to have a direction that goes with it, right? Even though we said work was scalar, we say we have negative work or positive work. So I still want you to think about it in terms of, am I gaining or am I losing? But it just doesn't have a direction necessarily that is associated with it. Okay. Okay, do we have what we need on that one? Okay. Let's go ahead and try one here. Okay, I'll give you a couple minutes to get written down what you need to. Okay, does anything here kind of stand out to you? The grams, right? So what does that have to be converted to? Has to be kilograms. So we need to take mass from 145 grams to kilograms. So we would divide by 1,000. Which would leave us with 0.145 kilograms. okay, is thrown with a speed of 25 meters per second. So that means our velocity is 25 meters per second. Okay. How much work was done on the ball to make it reach this speed if it started from rest? So that means this velocity, is it our final or our initial? Started from rest. So this is our final, right? And our velocity initial, oh sorry, you guys' book doesn't use F and I. Okay, so velocity initial would be 0. Okay, so when we do our algebra here, we're going to say that work is equal to change in kinetic energy, right? So I'm going to say work is equal to 1/2 m 25 squared minus 1/2 m times 0 squared, right? I forgot to plug in my mass here on the first one. And if my whole initial velocity is 0, right, I just leave out that term. Okay? Oops. Not 90, 45. We get about 45.3 joules. Okay.
So whenever it starts from rest, the kinetic energy is equal to the amount of work done?
Yeah. Okay. When it starts from rest, right, its initial kinetic energy is 0. So the change would just then be equal to the final. Okay. Questions here? How much work is required to accelerate a 1,000 kilogram car from 20 meters per second to 30 meters per second? Okay, so if we're anticipating here, if we're thinking about the result of our net work, would we anticipate our net work to be positive or negative? Positive, right? We're gaining energy, so work is being done. Right? Positive work is being done. So I would say work is equal to 1/2 m final velocity squared, right? It would be really easy for you to plug in 20 right there. Okay, minus the initial. What force now is required to move a 3,000 kilogram truck from rest to 32 meters per second over a distance of 4.5 kilometers? So now we're taking the fact that we know work is equal to change in kinetic energy and work is equal to force times displacement, right? What can happen algebraically if we have two equations set equal to the same thing? They can equal each other. Okay? So we would just take change in kinetic energy equals force times displacement, right? And you can do it in 2 steps, right? You could solve for work first and then go through and solve for your force. Like, that's fine. But if you are okay with combining it into one equation, like at the beginning, that's great. Okay, so I'm just going to work from this equation right here, this last one. Change in kinetic energy would be final kinetic energy minus initial. And what's my initial kinetic energy here? 0, because it starts from rest, right? So it can't have any kinetic energy if it's at rest. Okay, I'm solving for my force, and my displacement is what value? Yeah, we got to change it. So 4,500. Right? We want to take that from kilometers to meters. So to go to meters, we would take it times 1,000. Okay, do we see where all those numbers came from and why they're going where they are? So we talked about kinetic energy, which is the energy of an object in motion. Now we're going to talk about potential energy. So what do you think potential energy means?
Stored energy.
Yes, stored energy. That's a good way to describe it. Stored energy. Okay, energy associated with an object that has the potential to do work on something. Okay? Sorry, I didn't give you the definition that was up here. Okay? Potential energy, it's really important for you to understand that potential energy depends on the position of our object. Okay? It depends on the position of our object. So what that means, right? We're talking about really gravitational potential energy most generally, most often, okay? Gravitational potential energy depends on the position of our object, okay? So if my calculator is 6 inches off the ground, does it have the potential to do a whole lot of work if it falls? Not a whole lot, right? In comparison, if it was 6 feet off the ground, does it have the potential to do more work on an object it would fall on? Yeah, okay? So that's how we can kind of judge our amount of potential energy, is basically how far it is off the ground. The higher you are off the ground, the more potential energy you would have, right? Because when you impact something that's on the ground, you would have greater potential to do work on that object, right? Apply the force and displace that object. Okay, does that kind of make sense? So the higher you are, the more potential energy you have. So if a brick's held in the air, it has more potential energy because of its position relative to the earth. So the higher we get, the greater amount of potential energy. That's essentially it, right? It has the potential to do work on an object it would fall on. Okay, so this is gravitational potential energy. We're going to look at gravitational potential energy and spring potential energy, but this is going to be the very most common form that we'll look at. Okay, so here's our equation for potential energy. Okay, gravitational potential energy. And again, usually I'm going to leave this G off because we use potential energy most often for gravitational, and it's got gravity in it. So that's a really good clue that it's for gravity. Right? So mass is here in kilograms. This is gravity, which is 9.8. And this is Y. This is our height. Okay, so that has to be measured in meters. And this is where it gets tricky because it's not a vector, right? Negative 9.8, you don't have to use it. You have to just use regular 9.8. Okay, so that's kind of unlike what we usually do. Okay, so but you can just use regular 9.8. Okay, so there's our gravitational potential energy equation. That should go on your equation sheet. Okay, higher off the ground an object is, the greater Y is, which means greater amount of potential energy. Okay. The negative is here, again, just telling us that it's moving downward because it's work done by gravity. So even though it's a scalar, right, we're still thinking about it moving in the downward direction. So this equation is used much, much less often. Okay, I wouldn't even really maybe bother putting this one on your equation sheet. You could think about maybe putting on this one, right, work is still equal to change in potential energy. Give it a basic one, but I don't need you to go into the change in potential gravitational energy. So this right here, I would go ahead and put on your equation sheet. Okay, so the work is always equal to the change in energy, right? It was equal to the change in kinetic energy, and it's going to be equal to the change in potential, okay? Your book explains this work done by gravity, but I want to think a little bit more in terms of the net work, okay? So I would just go ahead and put on this a little bit more general, okay? Okay, so it says it goes from point A up 10 meters to point B. So here's 10 meters. And then it plummets a total of 25 meters to point C. So what's the difference between here to here? 15, right? So in these problems, what we're going to do is we're going to really kind of set our ground level at where our object starts at. Does that kind of make sense? So you can do it a couple different ways, and it'll always work fine as long as you're consistent throughout your problem. You could choose always at the lowest level as your ground level. You can choose your starting point to be your ground level. You just have to be consistent in terms of, is it landing below or above where it started? Does that kind of make sense? Okay, so it says relative to point A, so that means we want to use A as our ground level. Okay, so from A to B, are you gaining potential energy or losing potential energy?
Gaining.
You are gaining from A to B, right? You're going higher, so you're gaining potential energy. So at point B, our potential energy would be mass times gravity times our height, right? And that's it. Okay, which equals 98,000 joules. Okay. Now at point C, it wants it to be relative to point A. So it's not like we're going necessarily from B to C. We're going to go from A to C. Okay. So from A to C, we would go potential energy is 1,000 times 9.8 times, what's our height at point C now? Negative 15. Because as we go from A to C, are we gaining or losing potential energy? Losing potential energy. Yeah, that's right. So now we want to go from point B to point C. So we would say we're starting from B to C, and we know the difference in height here is 25 this time. So our potential energy change would be mass times gravity times negative 25 this time. So we should have a greater change in potential energy because we're going that extra 10 more meters, right? Any questions here? Other type of potential energy that we're going to look at is potential energy in springs or coils. Okay, so as we look at a spring, there's a couple terms that you just need to know here with our springs. Okay, so potential energy of a spring is going to have its own specific equation that will really differentiate itself between potential energy of gravity. So you'll know the difference just based on what the equation looks like. Okay, so in our coils or our springs, what does static mean? Yeah, at rest, right? It's not moving. So that means it's not being, pulled or pushed. Compressed means we've done what? We pushed it together. And then stretched means we've pulled it apart, right? If we stretch or compress it, what does it want to do when it's let go? Go back to its static position, right? It wants to get back to its static position. So when we compress and we stretch our spring, we now have a form of potential energy, right? Because if we compress it, and we release it, it would have the ability to do work on an object that it comes into contact with, right, and displace that object. The same thing is true for a stretched spring, right? It wants to do work on an object when it compresses. Okay, so to find the potential energy of an elastic spring, we're going to look at the force that has to be exerted, right? So to put potential energy into a spring, we have to exert a force, right, either push or a pull to get it to that position. Okay, so here's one equation that we can use for springs. So force is equal to K times X, and K is what we call a spring constant. Okay, and it's a little bit, it's kind of a lie because it's not really a constant. Okay, but the spring constant tells us basically how difficult the spring is to stretch or compress. Okay, so each individual spring has its own spring constant. Okay, so it's really not a constant. It's more of like a variable, okay? But that spring constant tells us basically how difficult it is to stretch or compress. So K, anytime we see a K, means we're going to be dealing with springs. Okay, that's something that you should understand. Anytime we see a K, you should be thinking springs or coils. Okay? I don't want to talk about this right now. Blah, blah, blah. Okay. So when we find the potential energy of a spring, we're going to look at using K again. Okay? So the potential energy of a spring is given by this equation. This is one that should go on your equation sheet along with that F equals Kx. Okay, both of those should go on there. Sorry, I didn't really explain what X was. What is X? What do you think that probably is?
Like how far you should?
Yeah, it's distance or displacement. So sorry, I didn't give that variable on the first time. But in both cases, it's its displacement. And it needs to be measured in meters. So you're going to probably need to convert on that pretty often because usually a spring is not meters long, right? It's little. So you'll probably have to do some converting with that.
The first one was F equals K?
F equals Kx.
Gotcha.
Okay, so both of these need to go on your equation sheet. They are for springs specifically. So anytime we see a K, that's our spring constant.
Isn't it negative F? Or
Okay, the second one that we looked at, I kind of skipped over, was a restoring force. That's the force that bounces the spring back. So we're not really worried about the opposite part of it yet. Okay, so this is the force that would be applied to make it stretch or compress. This K value, if we're going to put units on it, right? If we were looking at the units for this equation, we would say newtons equals K times meters, right? So if I'm going to get K by itself, it really has the units of newtons divided by meters. Okay, so K units are newtons divided by meters. Okay. Spring is compressed 10.5 centimeters. If the spring contains 0.86 joules of potential energy, what is the spring constant? Okay. When we deal with our displacements here, usually you would think of, here's our spring in its static position, and when I compress it, right, my x would really be a negative value because I'm pushing it to the left. But in our potential energy equation, we're going to square that displacement value anyway, so there's really no need for us to put in that negative. Does that kind of make sense?
Yeah.
So when we stretch it, we'd be thinking of it as a positive displacement. If we compress it, it's a negative when we're talking horizontally. But since we square that displacement value, there's no need for us to put that negative in there. Just something to think about. Okay, so potential energy equals 1/2 kx squared. Tells us we have 0.68 joules of energy. We're solving here for K. And our x value we need to turn into meters, right? Convert to meters. Okay, so that would leave us with what value in meters?
0.105.
Good, 0.105, right? Divided by 100. Okay, and we're just going to square that term. Take that times 1/2, and then you can divide that over